Good morning to everybody. Welcome to my channel. And today we introduce a theme that is introduced by Sina Java Osdel, that is the geomechanic product manager of slide 2 and slide 3 of rock science. He introduced in recent post in LinkedIn a new feature, interesting feature in slide 2 software. For example, the feature is related to consider the direct sliding at interface between geosynthetics and soil in reinforced soil earth structures. During the verification of the stability of the slope and in the structure. Internal verification, local verification, of course, I suppose the global verification of the stability. In the post is synthesized the message related to the heuristic weak layer handling feature of the slide 2 software, that is an excellent software that is available for the technical communities in the world. This is the original image that Sina posts about the characteristic. For example, is interesting the possibility to consider sliding along interface, activate or not activate during the analysis. This the direct sliding at the interface is a well-known phenomena and of failure for reinforced earth structure. Well known since decades, but very few software consider in the global analysis of stability. That in this case, I suppose. Well, we introduce as well what's happened with SSAP software. That is, I remember, is completely freeware software for the scientific and engineering communities in the world that have the possibility since a long time ago to have a lot of tools to make slope stability with advanced limit equilibrium methods. We move rapidly with the documentation of the available directly from the software. And then, in particular, in the reinforced earth documentation. This is the last version, latest version of the documentation manual, where described a lot of interface phenomena between reinforced earth geogrids and geosynthetics and soil when we have a reinforced earth structure. Of course, the pull-out resistance, but not only the pull-out resistance, because exist other kinds of interface. For example, one of the puncture, local puncture, external puncture, and one of the most important determinant for the stability is well the direct sliding phenomena. That is considered the weak interface between geosynthetic and soil. Well recognized methods, so is in the design we have to define a direct sliding coefficient and considering the possibility to generate around the geosynthetics, geogrids on geosynthetics, a shear band, weak shear band that can produce anomalous sliding surface with a prevalent planar extension. Of course, the FDS coefficient must be at the level of design directly evaluated. It's not so easy because it's not given explicitly from the producer. So you have to define it from the geogrids characteristics or geosynthetic characteristics and define. SSAP gives us the possibility to, in the manual, to have a lot of nomograms, and all the set of equations can be used to calculate the FDS. That is, depends from alpha S and FSF that is given usually as the skin friction coefficient as well. So this nomogram that I produced from existing function and might be used to evaluate the different components and also, for example, the bending factor coefficient as well for different kinds of geosynthetics. We indicate the necessity to use, anyway, to use the direct sliding to evaluate with special search engine that is available from since a long time ago. Well, this is the case, design case project in Italy of same years ago, where we have a slope made, an excavation made on design of excavation in a slope with glacial till deposits and with colluvium deposits just below existing edifice. But what is the problem, or in this case, was determine what are the level of stability of this excavation. For example, we have very weak material without cohesion, and the glass is we have 28 of colluvium material here and 32 with 5 the cohesion for the glacial till, and a substratum made of rocks that is modelized with GSI criteria. Of course, running the simpler methods of evaluation of with convex random search, that is a brute force engine based on Monte Carlo analysis, of course we found rapidly very low condition of stability, practically totally unstable. But so we did the possibility, the hypothesis was considered to reinforce these kinds of excavation, making a berm of reinforced earth just in front of it. Of course, in this case, we have we haven't reinforcement. This is one of the simplest cases for slope stability analysis. Of course, the groundwater is at the interface between rocks, bedrock, and glacial till. We can show all the surfaces that have safety factor less than 1.1. It is the limit considered from the rules in Italy. We can see that we have two families of surface. Of course, the colluvium, unstable and unreinforced colluvium in the top of the slope, and material here we have different kinds of safety factor and shapes. Of course, no grid search and no exclusively circular surface are considered, even if some of them have a circular shape, more or less. But the convex random search is limited to circular surface only, but also other. Of course, we see that the slope with two type of families of potential sliding surface with unstable condition is totally unstable. So you can also see now the map or local safety factor based on hybrid methodology between LEM and FIM that can be used by Kupat algorithms. At the end of the analysis with limit equilibrium, advanced limit equilibrium methodology with Morgenstern price, we can look that exist 2-3 red zone where the instability can start with, for example, process of progressive failure, or probably not so progressive as in the top of the slope, because we have the worst condition. Well, now what we can do with SSAP during the design of reinforced earth methodology. First of all, what's happened in the SSAP? SSAP have a long history of evolution and development. Of course, is completely free, and you can find the new and bug fixes chronology since 2010, and then you can see what's happened. Then, if you move and 2019, in the September of 2019, exactly 4 years ago, we can observe these kinds of situation. In other terms, you find that the simulation and verification of the direct slide phenomenon in reinforced earth structure. We modified convex random search and random search engine, but especially we change the sniff random search, that is a difference with the convex and random search that are brute force methods Monte Carlo, generating sliding surfaces samples and the sniff random search is, I showed in the video before, is a search engine generating potential sliding surface based on geotechnical intelligence. Completely different. It's not an optimizing algorithm, for example, Kuko search and similar, but is based on a method that identifies and tracks preferentially the potentially weak layer inside, even if they are centimeters of depth. And this is extremely useful when we use it for the to to simulate and verify the directly sliding possibility and phenomena between in the interface, weak interface between the geogrids and or geosynthetics and the soil, the filling soil in the reinforced earth structure. So this is important. This is the version that we translated with automatically with Google translating possibility, because the part, this chronology is in Italian, but you can find acceptable in English automatic translation. This is the first version in the made 4 years ago, and since this we have a lot of changes, improvements, correction, and some of that in a lot of available tools. You can find the chronology with the last modification. Okay, now we look what's happened with the design of the new model of slope with reinforced earth. So we constructed a reinforced earth in Italy. This is the design in the North Italy, very close of the Appian Alps, inside the Appian Alps, because this is based on substratum of glacial till deposits and rocks, bedrock of gneiss metamorphic rocks. Each one of the level in the berms is practically reinforced level of geogrids, and the filling have a design value of 33 degrees of angle internal friction. The external slope of the berm is 38 degrees. And these parameters of the rock bedrock with GSI methodology in continued domain for rocks. So it's very strong bedrock. I show you the file contains the data of the geogrids. We have the coordinate of left portion of the geogrids on the geosynthetics. We have different level of design tensile strength value, and the bearing coefficient FB, the equivalent FDS coefficient, or direct sliding coefficient, for each kinds of material. Now, of course, we have also the wrapping, left and right wrapping, and the puncture coefficient. Details on this case you can find on the manual that I showed you before. You can find details on these design parameters. Okay, we activate the sniff random search that I remember is not engine that based on brute force generation of sliding surface, but engine that can feel, identify and trace the potential weak layer inside the structure. For example, the interface between grids and soil. Each level of reinforcement, because we have a lot of them. We can use one of the available rigorous methods, because simplified methods are not considered, because not effective, not sure when we have reinforcement on any kinds of reinforcements. with other types, not only for reinforced heart. We activate some option to consider and then we can start the analysis. Of course, this method, this engine, is not fast like the pure brute force methods, but have several advantages. For example, the possibility to identify and trace much faster and with level of reliability much more higher with respect to other kinds of search engine. For example, we can see that we arrive practically very close final results 1.27 in less than 2000 surfaces. 1 minute maybe. Look at the surface we identify. You can find that are not circular one and are based at the, for example, the interface between the 8 centimeters from the interface of the in the soil and the geosynthetics at the base, because we are the strongest geosynthetics at the base, but also the weakest area because the sliding direct coefficient is the lower. For example, because we have a FDS of 0.6. But you can see that the surface, the sliding surface, are not circular at all. During the time that we view the graphs, the temporary results, of course, the program, the software continuously run, don't interrupt the verification. So we have the possibility to generate a concurrent process. For example, we can see that evaluate the progressive evolution of the results. We can see that we have the surfaces that we are show only the 10 surfaces with lower safety factor identified, even if are 1,000 more, and also is analyzed also the surfaces that pass very close with the other reinforcement as well. But at the moment, the lowest safety factor is oriented more or less at the bottom, where also exists the higher stress with respect to the wall, the slope. We wait 1 minute more just to have more reliable results, because it's important in this phase made. Of course, I remember the complexity of the model may affect the time required for the processing. Of course, also you can use also a fastest personal computer or desktop, and of course the choose of the engine we use to generate this one is the real-time safety factor for different kinds of surfaces. We are more or less arrived at the end of the processes. Also, we can use more time, but we stop here. We can show there is the final result of the 10 lowest safety factors surfaces. So we have a clear shear band, just below or just above the interface of the with evident dominant planar extension and general not circular surface as well. Of course, we have adopted here special kinds of spline smoothing, but also we can avoid the spline smoothing of the surface, but it's affected a bit only. This is the map of the safety factor generalized of the wall slope with the reinforcement. Of course, we can see that the distribution internal value of safety factor is not homogeneous, but of course we have the same pattern, planar pattern, due to the effects of the interface. But the global is 1.23. That is considered acceptable with for the rules in Italy, because the parameters as design parameters are considered the limit state design following Eurocode 7 and the norms that is indicated from Italian rules that have some similarity with, for example, LRFDI American. But what's happened if we repeat the analysis with the brute force engine, for example, convex? The same parameters, same model, don't change it, of course. These are the same parameters, same geometric grids, and convex random search. So brute force method. What difference with the previous one? Better? Worst? We see. This engine is extremely fastest with respect to the others, but you can see that even if we arrive at the same value, we have the safety factor is not arrived so low that the before, because in this case, even if in case of the surface pass very close at the interface between the geogrids and the soil interface, or inside the interface, we have the possibility, for example, in this case, but don't identify so easily. This is another possibility, of course, not circulars and prevalent, but without the sniff random search, you can trace preferentially this kind of weak layer that are at the interface between the soil and geogrids. This engine is, of course, fastest with respect the fastest possible, but in this case of reinforced earth is better use the sniff random search. Of course, we have considered in this kind of analysis also the global stability of the structure, because, for example, the bearing capacity of the soil below the berms of reinforced earth should be considered during the assessment. Of course, don't appear the surfaces that are in the bedrock, because the safety factor is much more higher than we found now. So we arrive more or less at 1.42, 1.41, higher than the previous 1.23 that is considered with sniff random search. Even if exist some surfaces that can arrive to follow more or less the interface, but not so well as the sniff random search should do. We arrive at the end of establishing the maximum number of surfaces generated. Of course, I remember that you can generate with SAP until 99 millions of surfaces. If you want weight, you can do that, no problems. But usually it's not necessary to arrive at this amount. But 10,000 or 15,000 is enough for our case. You can see the final results, of course, 1.42 to family of potential surfaces, but in this case is not, some surfaces can resemble circular one. I remember that circular one is not generated preferentially. Any shape of surface compatible with sliding is accepted. And now we see what's happened with the map of local safety factor. You can see that exists a similar pattern with respect to the other, but a little bit different, because we have some pattern similar to the other one when we have the horizontal effect of direct sliding, but the situation is much more stable with respect to the other. Well, what consideration we can do that at this point? Many consideration, for example, that SSAP is not commercial, of course, software, so you can use it freely. We have a license completely free for students, didactic activity, research activity, professional activity. Of course, a lot of engineers use it in Italy. We have more than 1,000 users, civil engineers, engineering geologists in Italy that use this software. Some of that from a long time ago, and also, of course, in the design, global stability analysis of reinforced earth structure that at the end are approved from the authorities that survey that the design and the project is follow the established rules for this kind of job. Of course, is not the technology of sliding management or sliding stability is not a newcomers. Of course, we know in the literature that exists a lot of evidence and methodology indicated for considering the instability. Also in previous software, but software that manage only local stability of the reinforced earth. Instead, we can also consider the global stability, but the world effects of the direct sliding, because the limit between local and global is not defined. This is an important issue. Don't consider enough in the literature of stability of slope, and in particular with reinforced earth structures. Of course, we can have a software, a slope with combined kinds of strength criteria, materials with geomaterial difference. For example, rock mass with fracture or continuous on discontinuous structure, and then we have the possibility to have combined with other kind of materials. So manganese with substratum with liquefaction possibility, and above geogrids or reinforced earths. So should be considered all these cases, and most of the local software stability analysis, for example, some of the excellent software made from the production of geogrids geosynthetics don't consider enough the possibility to combine different materials and strength criteria in the same slope. Slope do that. SAP do that. Can the SSAP do that from a long time. And of course, consider since 2019 direct sliding in the calculation on instability, global stability of the reinforced earth slopes. Of course, I invite you to see the official web page of SSAP for evaluate the numbers of features that are present in the software and the level of evolution of it with respect and compare with other software, freeware software or commercial one. Of course, each software that you can find in internet have their own feature and their own capability. SSAP have their own features, and most of their feature has evolved with the help of the user, the final user. A lot of final user contribute in this kind. In the manual, you can, for example, we have the description of the rock mass characteristics are considered, of course, the GSA, but method and criteria, but in the general Eke-Brown method with nonlinear methodology, with the possibility to define locally the parameters depending from the stress present, and also a criteria to GSA is described in the manual, so I can invite you to read this one. You can activate the translation, automatic translation should be give a excellent or acceptable translation level in English or in other languages. We have all the parameters of GSA are described and can be with some example. For example, the non-linearity of equivalent cohesion and angular internal friction internal soil mass, because it's different from the state, and the possibility to insert discontinuity level and combine GSA with Barton JRC to consider the structure present inside the rock mass. Of course, you have also a special atlas of image to evaluate, in special case for flysch formation, the GSA value in qualitative way. Otherwise, we can use the method presented for quantitative way of GSA determination. Okay, many thanks for your attention, and I show you a future video on SSAP characteristics.